hour. Like a month ago, I came to about like 3:30, and I don't think there's as much going on as in the other area.
Okay.
Are you gonna be there?
Yeah, I'll be there. I'm not presenting anything with drawings.
Like have a poster.
Nice. Is that your master's project?
Mm-hmm.
Nice.
Yeah.
There's so much HIV stuff.
There is. There's so much.
It's kind of cool, like seeing the sessions and like seeing what's kind of a priority.
Yeah.
There's like no CBD stuff. It was like one session this week, which I was really surprised about. It's a lot of aging stuff. Which
I like got that app and I've just been like adding posts.
oh, I didn't check out the
favorite
app.
stuff.
Yeah, I was doing that online, so hopefully it'll transfer over to them. I can do it again.
Yeah.
But yeah, I'm pretty excited about it.
When are you getting there?
Friday night.
I'm getting there Saturday morning.
Okay.
And then
Oh
I'm
wow.
staying until Tuesday.
Oh well, I guess you can leave here at like. You
Leaving
can
here
catch
at
like a
8
6
a.m.
It's like let's see, 6 hours. You can get there by noon, right?
Yeah,
you
actually
land
my
by
flight
like noon.
here leaves at 8 and I arrived there at like 10:30 a.m.
Okay.
Remember when? Let me know what you're up to.
Yeah.
My like best friend from college went to our MPH from Berkeley is gonna be there. We're like splitting a hotel room.
Oh nice.
And she's a poster too, so
Nice. April's part of the MPHA like national.
I feel like I saw her name.
Yeah, she's part of the mentoring. She's the mentoring chair. So she does like there's like a speed mentoring event that she's helping to run. Yeah. So she was like helping me with all the acronyms and the schedule. I'm like, what is this?
Yeah, it's intense.
But yeah, it's good. It's a really good conference here. Studying HIV and infectious disease.
Yeah, and I also am interested to go to a lot of the like substance abuse sessions.
Yeah,
There are also
there's a lot of
alcohol
alcohol,
and
smoking.
It's like they have a lot of alcohol. Yeah, there's a lot of alcohol and
Alcohol.
smoking.
Yeah, it's not.
Alcohol and smoking.
I suppose you could call it research. But,
That leaves it at.
It's observational.
yeah, exactly. Participant observation. I like it.
Morning, Jess. Sorry. I like to create a buffer between me and
Oh,
Jen.
that's okay.
Yeah.
I like to do that too.
It's like, let's do a little wheel around.
Too. I don't like when they're all touching.
Is that a new planning?
No, it's the only one I have, but it's kind of old.
It's good.
just a few announcements before we get with one of my favorite topics, which I've been struggling with for many years on my dissertation, is I guess two categories of things. One is the homework has been pushed back to the 7th, so it's like the Friday after next, I think. So we're making it a lot simpler, so hopefully it shouldn't be too bad. But let us know if you have problems. Next Wednesday is going to be open project time. I was also going to talk about Git, but I'll actually be at APHA, so I will not be teaching that. So, feel free to come and talk to other students. But if you want to work on it on your own at home, that's fine too for next Wednesday. And please make time. Reach out to us to make time if you need help on your project or if you're stuck. Also feel free to consult your peers, whatever resources you can find. So again, today's topic, multi-level model. Oh, sorry. Oh yeah.
Sorry,
No problem.
I think maybe it's because I missed the first couple classes, but for the project, are we making a poster and are we actually printing it and is there some type of like poster day or I'm not sure.
Yeah, that's a good question, and that's actually the third announcement, which I forgot, so I appreciate that. But basically, yeah, so everyone's gonna print a poster of what they've been working on. Hopefully it should be something that you already need a poster for. So the idea is not to duplicate work, but yeah, we're gonna have a poster day, I think, where we have everyone, talk a few minutes about their poster.
So we'll take this format of spotlight presentation format. So you'll present for 3 minutes and then have 2 minutes for question and answer session. So it'll be really quick, but it's kind of a good practice for some of the conferences that we.
Are we doing that in here?
Yeah, I think so.
Yeah.
We'll probably just, there's sort of like, I'll bring clothespins or something, and we'll just pin them up here and do them in sequence. Or, put as many of them on the walls as we can.
Yeah.
I guess, maybe I can talk and see if Valerie has another room, or we can find a room, but it's probably going to be difficult with everything going on.
At first,
this
I was
point.
thinking actually doing it electronically, so that will save you time from printing. But we'll discuss more about that and then see which format will work best.
Yeah. Sounds good. Any other questions about logistics stuff? So just, one final reminder, we're kind of at the special topics part, so feel free to tune this out if you're not interested in multi-level modeling. But I encourage you, it may come up one day, so this could help you get started with it. So just as an overview, I'm going to talk a little bit about what multi-level modeling is, all the different things people call it, and how no one agrees about what to call it, and why you would want to use it. I think most people agree on why to use it. I'm also going to talk about, in general, what are the types of multi-level models. Again, the terminology can often be different if you're talking to a statistician or a biostatistician or a sociologist or an economist. So if you're often, when you're trying to find research on your own, it can be confusing because people use different terms for sometimes the same thing or the same terms for different things. But I'm going to talk about the way that I think about it. This is an introduction, but again, take that with a grain of salt. This is just what I've made sense of it, or how I've made sense of it. And then I'm going to talk about the burning question, which is how to actually do it in R. Again, I found that the hardest part of this is figuring out how to get started based on looking up the terminology, which is always different. And then I'll talk briefly about other considerations in multi-level modeling. This will kind of be a segue into some of the later topics we do, like social network analysis and GIS stuff, geospatial statistics. A lot of those approaches are really just a kind of multi-level modeling, but as you'll see, there's a different way of determining what the clusters are. So today we're going to talk about clusters that you've measured. So you've got what hospital the person went to, or what the person ID number is for multiple time sequence observations. So kind of think of the grouping factor or the multiple levels here as just clusters that are a categorical variable. Later we'll talk about distances between observations, which is where social networks and GIS come into play. So a couple terms you may have heard that are kind of referring to the same kind of thing. Again, different people that I've seen have published different schemas for what to call everything, and there's differences still. So I think no one's quite agreed what to call it, and I think it's a product of these being independently worked on in different fields, different groups. But all these kind of refer to what we're talking about today. You may have heard multi-level models, hierarchical models, fixed effects, mixed effects, random coefficient models, fixed coefficient models, nested models, and then, to be fair, GE is a little bit different. This is generalized estimating equations, but it's used for a similar type of thing, which is dealing with cluster data. So in my mind, all of these kind of point to the same nebulous concept of cluster data analysis. And I'll talk a little bit about what people usually mean by these things in a minute, but okay, so why am I going to bother with multi-level analysis other than it being cool and sort of being a useful rhetorical tool for making people listen to what I have to say? It's useful in general for cluster data. So most of the models we use assume that, among other things that we don't talk about very much, they assume that we have independent observations. And I'll get to what that actually means in a minute, but the idea is that these are independent units that don't affect each other. They can be considered separately. So multi-level modeling says, okay, well, we have some sort of structure in our data. Some things are related to other things. Some observations are related to other observations. And we have some information about what that structure is. And I'll call that clustering. So some of the benefits of this is, okay, well, maybe we're doing it the right way, but like, what does that mean? So really what that means is that you're improving your precision of your estimates. I think maybe it can reduce bias, but I'm not entirely sure. I think it depends on it, but usually you can increase precision. Because if you think about it, you're kind of putting more information into the model, so you're getting more out. You can also estimate effects at multiple scales. So if I want to know what's like the neighborhood effect versus the individual person effect, I could create measures for that. Now it's still open to interpretation. Well, is this an appropriate way to interpret it? Did I use the right kind of model to get what I'm interested in? But those questions aside, you could get a number out that represents different sort of levels of effects. And what I see as the most important benefit, and this is why I'm using it in my dissertation research, is you can use it to control for unmeasured confounders. So this is the golden, I see this as the golden fleece of epidemiology. We're always worried about confounding, right? But we have to measure confounders, and you have to say, oh, well, did I measure the confounder properly? Well, I can magically control for all unmeasured time invariant factors with my project, so I could just avoid that whole 30-minute conversation in my defense. Instead I'll replace it with a 30-minute conversation about how this does that, but, so it kind of evens out. But again, you can also consider like nuisance parameters as something else, kind of, things you might think about as confounders, but, they're not really confounders. Again, don't quote me on that, that's the way I think about it, but not Epi Department approved. But yeah, this is great. And so if you combine this with a way to handle time variant confounding, or like confounders that change through time in an elegant way, you can get really simple model that controls for all this stuff without you losing a lot of precision in the process, which is exciting. So that's really what I see as the real benefit of this in the epidemiology context. All right, so I talk about multi-level data. What do I mean by that? Like, what does it look like? Well, it's really just regular data, except you have an additional variable for like the cluster or the group, so it's like a category variable. So again, you've got the normal individual covariates. You've got the group identifiers, which would be the cluster data, and then maybe you have some covariates at the group level. So we actually already do this in regular GLMs, right? Like we might have things like neighborhood income that we just put into a model, often because we don't have the individual's income or something. Or we could put in environmental variables, which are really often group levels. If they're not, like if you're not measuring someone's personal exposure, you might be using an air monitor. Well, that's really a group level variable, kind of like this district's air pollution or something. So again, it's very similar to what you might see, except some variables can be at the group level, and you'll have group identifiers for the clusters. And you could have multiple identifiers, so you can have weeks within people. You can have hours within days, within weeks, within people, within neighborhoods, which is what my dissertation has. So it gets very exciting when you have lots of different levels. So I'm just going to briefly mention generalized estimating equations to talk about why you probably don't want to use these and why I won't talk about them too much. This is a popular way of handling clustered outcomes, but the way that I see it, this is sort of a more biostatistics approach. And what I mean is that it's kind of, it's kind of ambivalent about what I think the mechanism is. I feel like in epidemiology we spend a lot of time making decisions about models based on what we think about how the world works. But this kind of ignores that and says, okay, well, I'm going to use the most general approach, which is to think about, like literally think about observations as not independent. Well, if they're not independent, then they have covariance, right? So I'm going to estimate their covariance. So these are just some examples of what you actually specify with the GEE model. And these are covariance matrices, right? So what happens is, imagine I have 3 observations in my study. This could be like a person's 3 blood pressure measurements, or 3 different weeks of mental health or something. How good do I feel on each week? So the way it works is, imagine the rows and the columns as observations. So like column 1 is observation 1, column 2 is observation 2, column 2 is observation 3, and the same thing for going down. So the first one shows this upper left matrix shows a regular study, right? So in a regular study, individual observations are related to themselves, so that we put in a covariance of 1 to say that it's kind of the identity, right? And then we say that there's zeros for everything else because this observation 1 doesn't affect observation 2. There's no covariance. Observation 2 doesn't affect 3, right? So there's all zeros filled in. So this is the way that our traditional study works. But what we can do in GEE is we're going to say that the outcomes have some sort of covariance with each other. So here's one. I forget what these are called. It's not too important, but in this one, the idea is all the observations within a cluster. So pretend this is just like person 1's matrix. All the observations within a cluster are essentially the same as themselves, but then they have some covariance that's just a standard number that share between everything in the cluster, right? So in this example, maybe within a person, everything has a covariance of like 0.5 or something. I don't know what scale I'm talking about, but the idea is that things within a cluster are just more similar, and they're more similar by a factor that I estimate. So this would be estimated for the model, but I'm kind of fixing it to one number within each cluster.
Is that one called identity or something like that?
Yeah. It might be like
Autoregressive.
Yeah. This is. I think this is AR2 or something because it's like this. Yeah, this one's either autoregressive, like simple autoregressive, or something like that. I mean, you can just Google the GEE matrices and you can find it, but. In this one, this uses distance, so this will be more similar to the spatial stuff we use. So here, the closer you are relative to the other observations, the more similar you are, right? So pretend that rho here is like 0.5. So 0.5 here is going to be greater than 0.5 squared, which is 0.25, not 0.25, 25. Sorry. So the idea is as you move farther away, the observations have less covariance, and as they're more similar, they have more covariance. So 1 means I'm the same as myself, so that's the maximum. And then here's another one where I say, okay, well, I don't want to make any assumptions. I'm going to assume that for every person, the difference, the covariance between the first and the second visit is 1 value. The covariance between the second and the third visit is 1 value, and the covariance between the first and the third is another value. But it's the same for every person. So again, you're kind of applying, or like the degree to which things are similar is the same within people. So one example for this might be, think about 3 children in a family or something. Let's say there's a genetic condition. Well, that's a bad example, but think of something that has to do with the home environment. Maybe the first and second children are more similar across the population than the first and third children, and the second and third children are sort of similar too. So we'll get into more of this with social network stuff and GIS stuff, but this is literally, not literally, but this is essentially what you're doing with GIS stuff, is figuring out what's this kind of matrix. In GIS, it's often called a weights matrix, but it's the same idea. And it works a little bit different, but it's sort of think about how observations relate to each other, and that's the same concept. All right, so we won't model this today, but know that it's not that difficult. So I'm going to talk about what I see as the overall paradigm for doing all these models. And the way that I start with it is random and fixed effects. So let me just draw the regression that we're familiar with in general. Sorry, it's so small. But if you remember, I'm just going to call this y as our outcome. And we're going to say y equals beta 0 plus beta 1 x1 plus ... And then you have an error term, which we often forget about. But the point of this error term is that this like enables our model to work, and that's how we like estimate how sure we are about stuff, because you know it never fits exactly a line. So we use this to figure out, okay, well how sure am I about everything? How close does it get? And that this is just the difference between the predicted value, which is all this stuff, and the actual value. So the question we're stuck with is, okay, if I have a clustering, how do I deal with clustering, right? And basically, you can put it in wherever you want, and where you put it into the equation is what it's called. So I talked a little bit about GEE before. What GEE really does is says, okay, the clustering has to do with Y, right? So GEE is ignorant of all of this. It just cares about the covariance between the outcomes using that matrix. Now, fixed and random effects happen on the right side of the equation. And I'll start with the simplest one, which is having to do with the error term here. So this, so I'll say 1 is going to be error, or sorry, 1 was GEE, right? That says put the clustering inside of Y by using covariance. Option 2 is let's look at the error term. Right? So I want to use this right side of the equation. Now this is convenient because I don't have to deal with any of my other stuff, right? And this is the same across like every model kind of thing. Now the form of what this takes is different. So if I have like a logistic regression, this is different than, well actually the whole estimation is different, but you can think about this as being a different kind of variable than if this was like a linear regression or something, or if I log transform it, it's going to be different. So I'm going to try and put the clustering into the error. And so there's two ways to think about it. The first way is pretend that you have two error terms, right? You've got, so this will be A, and this is the random. Pretend you have two error terms. So each person gets, so this will be P equals the error of the individual plus the error of the group, or the cluster. So this is really simple. So this is saying, okay, each person has a deviation from like what I think the predicted value is. So we say, okay, well each group also has a deviation, right? So this is a pretty simple way to do it, and I use a similar machinery. You don't have to worry about it, but what the model is doing is basically using the same idea of fitting the individual error terms to determining the group error terms. And the other way I have here, which is, oh yeah, so think about changing the error. But another way to think about this mathematically is this is actually also changing the intercept kind of thing, right? Because you know, if I moved all the terms around, I could also rewrite this as like, and this is where things get confusing because different fields use this differently, right? I could also, so I'll put AKA. This is equivalent to having an intercept for each person and an intercept for each group. So what I could do is I could make a group level intercept. I'll call this B0 group. Right, but this is really the same as error group. Right? This is the same approach. Because I can just call it whatever I want, but it's really just adding like an extra error term or an extra intercept for each group because it's the same. Because it's just a linear equation. So what happened is people looked at this and said, okay, well, maybe, you know, I don't want to make an assumption about the distribution because the error term you always assume has some distribution, right? That's how you estimate your confidence intervals. So like in a linear regression, this is like a normal distribution. It's one of the assumptions. So what I can say is, okay, well maybe I don't want to make an assumption about distribution, and I want to be really lazy and use a regular model, right? Like a GLM function. So what I could do is I can say, all right, let's just let's call this fixed. And at its most basic level, fixed just says, okay, let each group have its own intercept and estimate them. And again, this is written a bunch of ways, but the way that I think about it, the simplest, is just basically, you know, each group has its own beta. So like beta 0, 1 would be group 1, beta 0, 2 would be group 2, beta 0, 3 would be group 3. So each group has its own. You can think of it as an error term or as an intercept, same thing in this case. another way to think about it is you just have another variable called group. And this is the way that you put it in any program. Well, let's just have something called xg, which is the group. And then we're going to multiply that by beta 0. Right, so this other way of thinking about it, so again, these are like, they're just mathematically, and this is why it's so confusing, is because there's so many ways to represent it. Just pick whichever one makes sense to you. So a fixed model either has an intercept for each group, or it has the group as a variable, and then there's a categorical there's a categorical variable for group, and then you're going to use some sort of betas to estimate it. So remember, when I put in a categorical variable, it kind of makes that matrix where there's like one estimate for like let's say I've got one of eye color, it'll have one estimate for green eyes, one estimate for brown eyes, and maybe blue eyes as the reference category. Well, this is the same thing. So it ends up estimating an intercept for each group, and then you can either have a reference group, or you can say, okay, let's pretend there's an overall intercept, and then there's deviations for each group. So again, just pick up on whatever makes sense to you, but this is, keep in mind that this is just an example of how everyone's doing the same thing, they just call it different stuff. So the third way to think about this is I've got a real beta 0, and then I've got individual beta 1. Okay, but the approach of all this is basically at the simplest level, fixed and random effects at the very simplest level involve changing, you can think about it as changing the error term or changing the intercept. So and then whether it's fixed or random depends on whether I think it follows a distribution, or whether I just want to say, okay, each one has its own group. So to the benefits, the random effect uses less degrees of freedom, right? Because I don't have to estimate anything. So the benefit of this is there's no estimation. So there's no loss of degrees of freedom. But the drawback of this is because you're not actively estimating this, you can't say what the difference between groups is, if that makes sense. So you're kind of saying, suppose there's groups, but I want you to take it out of the model. And I'm going to do that by assuming that the groups have a random distribution. So this, some people say this is better if your groups are a sample, but I don't really believe that. But the idea is, okay, well, if I sample the population at random, like let's say I sample all the counties in the U.S., well, maybe their properties follow a distribution because I have a sample, and then I can just say, okay, well, this is that distribution. So fixed effects, the benefit is there's no assumed distribution. So I see this as having lower bias, but you have to use up degrees of freedom to because you're estimating. Imagine if you have 100 people in your study, and there's only a couple observations for each one. Well, you need 100 degrees of freedom. You're going to estimate 100 coefficients for each person, and they're not going to be very precise because I have 100 of them. So another piece of guidance that I use is if there's a lot of observations relative to the number of groups. So random is good if there's a lot of groups relative to observations. Fixed is good if there's few groups. Or I'm more interested in the group effects themselves. All right, so again, this part is pretty uncontroversial, and everyone calls it different things, or they'll introduce the mathematics different ways, but it all comes out to be the same. And the key idea is, do I assume that my groups are a distribution, and that's the random effect, or do I want to estimate an effect for each group, and that's fixed? And you'll see in the code it's pretty easy to switch between these two. There's tests to figure out supposedly which one you like better, but or which one makes more sense. But again, I don't exactly believe that. But my personal bias. All right, so we've got fixed and random. The difference being how do I handle my group factor? Well, then I can take it another step forward. Okay, well I've talked about making my intercept, change for each group. Well, what if I want the actual coefficients to change? So what if so let's pretend this is like a drug. So changing the intercept changes the baseline prevalence, right? So I'm going to say fixed random at the first level. So this is the intercept. This is the baseline prevalence is different. Differs between groups. right? That's all that I can really get out of this. And that's fine in a lot of cases, but what if you actually think the effect is different? So what if I think that neighborhoods, like let's say I have some sort of intervention. So I'm gonna give neighborhoods $100. Everyone in the neighborhood gets $100, right? And I wanna see if this affects their health, some health measure. Well, clearly, this is gonna have a different actual effect on people based on like the income of the neighborhood, or really their income, right? So if I give $100 to people who really need it, it's different, right? So I actually believe that the beta coefficient changes between groups, right? And maybe this is really interesting. So if I'm doing unconditional cash transfers, I really care about the beta effect in certain groups, right? Because I'm probably going to do that with people who really need it. And conversely, you could do this to make an argument that if you do unconditional cash transfers, maybe it should be based on income, which seems, obvious to me, but maybe you need to prove it. Or maybe you want to give it to everybody, but the idea is there's some effect that's actually changing between groups, and you're interested in the difference of the effect. So this is the same as what we just did, except instead of changing beta, so let me just, this was approach 2. Now we're actually going to affect this. And this is where, I call this, there's still sort of random and fixed effects, but you'll see this as random coefficients or fixed coefficients. And I just refer to these as like mixed or multi-level things, because at this point you have a lot of flexibility, because often you'll combine approaches 2 and 3. 1 has to be by itself. You can't combine GE really in a meaningful way with other stuff, but at least not in a way that makes sense to me, but you can combine 2 and 3, and this is why the terminology gets crazy, is because people basically pick certain special cases and call it something. Someone else picks another special case and calls it something, and then everyone's confused. But the idea is you can act on these individual coefficients. So the coefficients themselves can change between groups. And again, the 2 ways to do it are, 1, I'll call it A so that it's parallel. A is, it's random, right? So there's a random, the groups are randomly different. So the way this works is, let's say there's like a real beta. I'll call this beta 1R. I'll put a double beta or something. There's like the true beta, and then every group randomly is different from that beta. So this is kind of like, another way to think about it is the population average beta and then the individual variance of the effect from that beta, and this is why it gets confusing. Yeah?
So when you're doing this, would you actually add more terms, like another beta vector and another X matrix for whatever you're modeling?
Yeah, that's going to happen. I'm just sort of, like R will do that for you. Kind of like you put in it in this idealized case where like, okay, I want this beta to be fixed or random, and then it populates out. But yeah, you're gonna have to add terms for each thing to like expand it. So yeah, I gotta be clear about that, because this is confusing because I'm mixing matrix notation and individual notation, so it's like, what's going on? But yeah, it's gonna have more terms. It's gonna need to be expanded. So like for this, for instance, you would, instead of saying beta 1 x1, now you've got like beta 1 for the population, and then you've got the individual betas. So this would be true beta 1, true x1.
Usually people use gammas.
Oh, yeah, that would be helpful. Okay, so gamma's for the group level
I think so.
effect? Okay. So we've got beta is like the population, and then what is gamma? This?
It's like a Y, yeah.
Okay, well this is, hopefully this is close to this thing. I don't know.
It's like an R, right?
Oh, yeah, that's like capital gamma?
Like a trident, or not.
Oh, okay.
Like a
I thought that was a
two spokes.
Yes, this is.
Yeah.
Okay, I'll just use this for now.
It's like
That's-
an R.
That's lowercase gamma.
Okay, that's fine. Okay, so I'll use this, and then I've got x, x1.
Everyone failed Greek.
Yeah. I just use the equation editor and I click on the thing now that I know what it's called. All right, so again, it's the same idea here. You've got the real, or the overall beta, and then you've got the group deviation. So in this example with income, maybe overall the effect of $100 isn't very big, but some groups have a really high value of this deviation from that. Like the poorest people probably need that money the most. So you can also do this with fixed effects, and then you're just estimating the individual group values, right? So that's the other approach. mirroring this approach is you estimate its own separate beta, right? And this is just an interaction term. You could think of this as the interaction between group and the beta estimate. So you've got, and again, this is going to generate a lot more terms, but just to sort of think about it as in the abstract of the interaction, you're going to have like beta, I don't even write, you know, beta 1 x1, beta 1 g x. Yeah, my notation and speech are breaking down, but the idea is you can use it, it's the equivalent of an interaction between the beta, or I guess really x1, so like whatever variable is affecting beta 1 and the group. Right, and there's different ways to write that based on what you're interested in. But it's the same idea where each group gets its own estimate. And so you have the same problems where you eat up degrees of freedom for all the things you're estimating. It doesn't work well if there's too many groups. And the random coefficient has the same idea. You can't estimate the individual group deviations. So actually, if I was interested in cache transfers, I might actually want to use fixed effects because I'm interested, or I could just do a substudy of people, you know, but maybe you want to pretend like there's some overall trend or something, but you know, the fixed effects allows you to like pull out the individual estimates for each group. The random effects tries to like get rid of it. You know, it does it more cheaply in terms of precision, but the trade-off is you can't estimate it. You can't say what it is. Now you get a distribution for these things. So much like in a regular equation, the distribution of the error can be used to determine the precision, or you know, at least do model diagnostics. Similarly, if I'm either estimating the xg, the EG, or the beta, where did I write that one? Yeah, here we go. Or if I'm estimating this, all these random terms, I'll get a distribution and a variance for these things. So that can tell me how important the groups are. So basically, if the groups are really important, I believe the variance will show up as really high, and if they're not important, it'll show up as really low variance, because it's like, this doesn't really do anything for me. No idea. So this is a bit of a mess, but try and keep in mind that there's really the main division is there's random and there's fixed, right? And then I can plug it into different stuff. I can make different stuff in my equation, random or fixed. And then people have different names for like, oh well, if you do it with this, it's called that. If you do it with that, it's called that. But they disagree. But this is what the least consistent is. What's the random versus the fixed approach. All right. So the final point of confusion is, maybe I skipped two? Oh, there's supposed to be another slide. Okay, somehow I've deleted a slide, but there's basically a mixed model. Is you can have both types of things, right? And you can mix them in any way you want. I can have a random, I can have a random effect on the beta, like the slope. I can have a random effect on the slope and the intercept. I can have just the intercept be random. I can have some things vary at different levels than others. I can have both of them occur for each thing. And we'll do some examples with the data set right now so you see what's happening. That you can really just put in whatever you want and get out different stuff. But the important thing is thinking about what you're producing. All right, so if you go on GitHub, I've got a script posted that you can basically just try out. And I encourage you to think about, okay, well, what if I put different stuff in here as fixed and random, like what am I getting out? Sort of look at what you get, and you'll sort of see like, oh, really the decision to make, or the decisions to make in modeling this are, what do I think is fixed? What do I think is random? What do I not care about in terms of group level stuff? And then and that's based on how you want to interpret stuff and what your data looks like. So this is on the website, but I'll just run through it for you. I'm going to use, there's a couple packages. Again, because people don't agree about this stuff, there's multiple packages in R to do this stuff, which makes it a nightmare sometimes. But I'm going to talk about one of my favorite packages because it's easy, called LME4. I also like it because the function can be pronounced Elmer, which kind of makes me laugh. But just keep in mind there's some similarities in syntax, but the ideas are the same. But often the underlying machinery that people have to do it is the same, but they just have a different interface. So we use LME4. You need to install it and then use the library to get it to work. And I'm going to use the chick weight dataset, which is built into R. So you use data chick weight to load it. And then let me actually just pull this out a little bit. So chick weight is a really basic sort of clustered type of data. There's other data sets in R if you want to explore or bring in your own. But the idea is that there's a bunch of chickens who were fed different diets and watched over time, and their weight was recorded. So if you think about it, there's sort of two clusters going on. There's the time period, because there's a bunch of chicks in the barn at once, so you can consider each time slice as a cluster. And there's also the individual chickens. So you could say, oh well, maybe I care about clustering by time period. Maybe the weather was changing a lot, and some time periods all the chickens grew really fast because it was great weather, something like that. Or maybe there was an earthquake and they all got their growth stunted. That would be a time clustering effect. Or maybe the chicks themselves, some chicks grow faster than others. Now, I don't think the chicks change diets, which is a problem. We're just going to pretend like they do here. So you can play around with multiple clustering factors. So what I did here is I've got some code that you can read about, but basically what it does is it splits up the chicks between different chick groups so that there's some represented in each group. I'll talk about what this does in a minute because it's a great example of after class if you're interested. But I'm basically just shuffling the chicks around to make groups here. So I'm making a group list that assigns, diet. I can't believe I typo in this. So I often create lowercase versions of everything that I'm interested in that's not in a data set because I hate typing dataset $. So I forgot to add that, but I had done it before. So I'm pulling out diet from chick weight in the local copy. I'm going to make a group list by applying the table function and repeat together and the rounding function to basically do the partitioning. Then I'm going to trim out, this line trims out the missing chicks so it's the same length. And then I'm going to use some unlisting magic to create a variable. But so you can read the comments and look at that if you're interested. But we're kind of done with data management at this point. But so basically what this produces is a C group variable which says, okay, what barn did I put each chick in, right? So the point of this is, let me make T group too. So I'm compressing the time group because there's basically too many chicks and too many time points and not enough data. So I'm making the groups larger by combining things so we can look at it. So the point of this is it makes us this nice, great, what have I done here? What is the length of diet? Clearly F. What? Why is diet only 4? Oh, that's why. It's the whole data set. Okay. Again, I hate the $sign notation. All right, so I just made a mistake about that same line. I was trying to feed in the whole data set into a table, and it didn't know what to do. All right, so I've got a time group. So I'll post an update, but this is the only line you actually need to fix. This is just make a copy of diet that's lowercase and not inside of a data set. All right, so the point of this is if we make a table, I want to make sure I have observations in every cross category. So here I've said, okay, I've got 3 time groups. So the time is in days, so this is like weeks. So week 1 would be day 0 to 7, day 7 to 14, 14 to 21. And then on the left I've got the chicken groups that I made. And so you can see there's fewer observations for week 1 and diet 1, but overall it looks fine. And this actually, multi-level model stuff can really handle different amounts of observations per person missing stuff pretty well. It might complain, but it'll still do it. And then here's one where I looked at the time group versus the diet to make sure that all those cells are filled, and that's true too. So again, this is just, I'm trying to make sure that you can actually do something with this data. Oh, and here's I'm going to pull out the response variable, so chick weight I also make into a weight. All right, so to start with, we can use a regular model in R, like a GLM. So here I'm saying, okay, what's the effect of diet on chick weight? Does feeding these chickens different diets matter? So you'll get the familiar GLM summary by using the summary function. And here I can see the relative importance of the diets. So diet 1 doesn't appear on this list, so I know that that's the reference category. I can see the intercept, which is kind of like, I guess, the grand mean in a linear thing, I guess. But I can see that maybe diet 3 is the best at improving weight. and the other diets are not as effective. Now, there's a bit of a limitation here because I have the weights, not the growth rate. So just pretend like the data set works, right? Pretend that this is just some variable we're interested in. If I really was interested in how the diets affect growth, I'd want to see what's the difference in weights between each observation. But you can see that just as a starting point to compare other stuff with, it looks like diet 3, is about 40 and has the biggest effect on weight. So this is nothing new, but we can use the Elmer function here, which has a similar syntax to GLM with one difference. So here's how I specify random effects. I use this vertical bar, and it's important to put it inside of a parentheses for whatever reason, because I guess it has to. I think the vertical bar doesn't have the right order of operations, so like you have to tell it, okay, specifically do it like this. And there's some examples in the help page if you forget what it is. But basically, what's happening is the left side of this equation is what varies by the cluster, and the right side is what the clustering factor is. So here, the clustering factor is time. So this is my weather example. And I have a 1 in there. Can anybody think about what that might be? So this is the name of some variable in my model. So here I've got weight and diet as other variables, but what is the 1? No, we're kind of treating T group as the ID. Close. It affects the outcome. So it's one of the things up there that that's not in there. No, it's not the error. Sorry, this is a harder question than I must have given less. So it's the intercept, right? So the 1 just means this is the intercept I'm estimating. So the intercept, which is equivalent to the error, right, based on what we just did. So that was actually correct. But the intercept varies between the groups, right? So here I'm saying I want to set it up so that I have a random intercept and a fixed slope of diet. This is another example of where the terminology breaks down. Diet is my effect of interest, but according to Elmer, it's a fixed effect. The thing that's confusing is, like, basically, diet is a group, right? Like, they are grouped in diets, and I want to estimate an effect for each diet. So in that sense, diet is a fixed effect, and I want to estimate it. So it goes, so in Elmer, everything that isn't inside of one of these vertical bar things is a fixed effect, and everything that is a random effect. So diet is a fixed effect, and I'm interested in it. And I can look at, once I run this function, I can look at the outcome, and we'll see sort of what's different from the GLM approach. So first, the effect we estimate is very similar here. So the time groups don't really matter, right? Because it's like there's not much of a change. But that's because I made them up. So none of these will really matter all that much. But maybe there's some difference because the chicks grow a little bit. But so here's the estimate is about the same. And then the other output I get that's important is this random effects table. So here I can see the variance for each thing that I'm estimating. So remember how I said one way to think about the fixed effects is having random effects is having multiple errors? Well, here's my 2 errors, right? So this is on 2. I forgot to put A. Oh no, yeah, A is there. So 2A, I've got residual equals individual residual plus group residual, right? Well, this is what this table is showing me. Again, you can interpret it different ways simultaneously. So the individual residual is 1662, and the time group individual is 4543. So to me, this actually suggests that the time is like somewhat important in terms of predicting stuff, but it doesn't seem to really affect the coefficient that we're interested in very much. Now, what would be interesting to me, and I don't know how to do this quickly, but I'm pretty sure if you added these together, you could find the equivalent measure in the GLM because it kind of adds up to the same number, I believe. Or some factor will be different or something. Or maybe you could compare the some sort of fit statistic or something. But there's basically you're splitting the original variance into the group level and individual level. And you'll hear people talk about variance partitioning, and this is what they mean. And there's some sort of things about, do I need a random effects model? Well, you look at basically the relative size of these 2 things based on your data size and stuff. All right, so that uses time group. Well, let's just, for comparison, let's use a completely arbitrary group and see what happens. So I group the chicks arbitrarily into chick groups here. So it's the same syntax, but I'm moving by chick group. If I run this kind of equation, I can look. I still get similar fixed effects coming out here, about 40 for diet 3. So it's not really affecting my coefficients. But if I look at my variance partitioning here, you can see the individual residual is really high compared to the sort of group level residual, meaning that C group isn't really that important. And again, you can feed this into functions to get out a statistic. I don't know if it's like a T statistic or something, but it's similar. You know, it's some kind of idea of like, well, under all these problematic assumptions about p-values that we make, you know, do I want to decide either way? But, you know, this sort of gives you a general idea of how important it is. So clearly, C group here isn't super important as a clustering factor. Now the good news is, if you want only fixed effects in your model, you can just use a regular model. You know, there's ways to do this differently, but basically you can just use GLM. So that's the final example in this section. Is basically you can just put in time group as a factor, and I get out the estimates for each time group. So they're also estimated here. Now the one thing I will add, so you know, you may be saying, well, what's the point of fixed effects, right? If it's not any different. Well, the trick is you can combine fixed effects with different estimation procedures, which is beyond the scope of this. But one example is conditional logistic regression. Conditional logistic regression, remember how you're kind of comparing like matched pairs or something to get. So what that's doing is it's a clustering factor, right? The cluster is the person. Conditional logistic regression is basically a fixed effects model with only 2 observations in each cell. And if you remember from the class, or if you're going to take it, the way they do that is by doing fancy stuff with the likelihood calculation. They basically they like cancel out a bunch of it and say, okay, well, we don't need to calculate this. That's what, you can do that with fixed effects too, and there's packages for that. You can basically say, okay, well, I kind of know that each group level intercept is going to be the same, or each group level like fixed effect is going to be the same. I don't care about them. I'm going to use math to remove it from my estimation procedure. And so you can do fixed effects with regular GLM, but you can also, if you find the package, you can get tighter confidence intervals because you can condition that stuff out of the likelihood function. And I can talk about that more if you're interested, but just know that you can always fall back on GLM to do fixed effect stuff, but there's also specific fixed effect packages that will give you the benefit of improving the estimation, with the caveat that you lose the ability to know what the fixed effects are. And I think I might have one more thing, but we're out of time. So here I was saying, okay, here's one where the coefficient is varying. So here the diet is actually different by time, and I get a very similar type of model. Here's my random effective diet. Is that right? Yeah, this is. Oh geez, yeah, this is the random effect of time on the diet. And then I also get the fixed effect of diet. So this is kind of like when you think about when you have an interaction term, you have like the term itself and then the interaction thing. You kind of can treat it as if it's both a fixed and a random effect, and it removes part of it. So I don't find this is super helpful, but I've seen some people claim that this is like the best way to do it is like give your model the maximum flexibility and try and get the benefits of both. And this is where you get into mixed stuff, is because you can kind of mix and match stuff as much as you want. Just one other point, in Elmer, if you want to have groups within groups, you can use, I think, the slash here and then say C group. This says chicken group within time group if you have like a hierarchical clustering. And if I'm lucky, this will run. And give me similar syntax that shows C group within T group. And these are cut off. Maybe? Yeah, it's just the table's on 2 rows, but there's C group within T group and then T group itself. So you can use this to make decisions about, is this a really important clustering factor? Do I care? Is this beneficial? So don't worry if this doesn't make sense, but hopefully this could be a starting point. I spent a lot of time trying to understand this, and I think there are classes here, but even if I'm not sure if they talk as much about how the terminology is different. I don't know, but I'm suspecting they have one particular interpretation of stuff, which could be an improvement in many ways over my approach. But this is where you want to get started. Is with this is try out Elmer, think about what's a random effect, what's a fixed effect, and keep in mind that you can have really a lot of flexibility about whether the intercept has those properties, whether the coefficients have those properties. And then if you really want to use GEE, use it for time series data. It works fine. Any questions? Cool. Thanks for your attention. We'll continue to have special topic stuff. And I think if we do this thing in the future, we might have people do a survey about what topics they want to do. But probably for like teaching eval as well. So I'll like ask you to put in, or maybe I'll just make a survey about like now that you know more about R, like what kind of stuff do you think would be more helpful for next year, or what topics are you interested in?